Okay, in this lesson I'm going to look at tree diagrams and the fundamental principle of counting. So a tree diagram just displays the different outcomes of each task in a statistical experiment. That's all it does. So we break the experiment up into tasks. What do we do first? What do we do next? And each of those gives us a level on our tree diagram. Remember also the number of ways a statistical experiment can be completed is equal to the product of the number of ways each task can be completed. We'll come back to that in a second. So suppose I want to draw a tree diagram for the following experiment. And the experiment is this. Flip a coin, a fair coin 3 times. So I want to flip a fair coin 3 times. And I want to think about that a little bit. And I want to draw a tree diagram. Actually, let me draw this, I kind of repeat myself a little bit here. We can draw our tree diagram kind of vertically down, or we can draw it across. I'm going to start by drawing a tree diagram vertically downwards. So I'm flipping a coin 3 times. There are 3 tasks in here. Task 1 is to flip a coin. Task 2 is to flip the coin again. Task 3 is to flip the coin a 3rd time. So task 1, can be completed in how many ways? Task 1 is to flip the coin. Well, the number of ways I can complete task 1 is 2. So I'm going to put 2 branches on my tree diagram. And we give those branches a name. The name is just whatever the outcome is. When I flip a coin, there are 2 possible outcomes. One is called heads, the other is called tails. The other thing really I want to include in my tree diagram is the probabilities of each one. So when I flip a coin, the probability that that coin lands heads up is 1 and 2, and the probability that it lands tails up is 1 and 2, assuming that we're talking about a fair coin. So that's task 1, flipping a coin. Task 2 in this experiment is to flip the coin again. And I think about it in this way. Look, if task 1 finished heads up, well then task 2 can be completed also in 2 ways. But if task 1 finished tails up, well then task 2 can still be completed also in 2 ways. So given that heads was the outcome from task 1, the 2 possible outcomes from task 2 are heads and tails. Given that tails was the outcome from task 1, there are still the same 2 possible outcomes. In fact, what happened in task 1 has no effect on the likelihood of anything happening in task 2. These are what we call independent events. Given that the first coin landed heads up, the probability of the second coin landing heads up is still 1/2. Given that the first coin landed heads up, but there's a still 1 and 2 chance when I flip the second coin that it lands tails up. And again, that's all the way across. A couple of things to note. If you look at the kind of grouped branches here, 1/2 plus 1/2 is 1, 1/2 plus 1/2 is 1, 1/2 plus 1/2 is 1. Those little groups should always add up to 1. So there's the first 2 tasks complete. You can see there's 4 different outcomes now. Heads, 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 tails, tails, heads, or tails, tails. There's 4 different outcomes for flipping a fair coin twice. But we have to flip it a 3rd time. So I'm going to flip it now again. A 3rd time. Heads, heads on the first 2 coins. Well, that doesn't really change what I can get on the 3rd coin. The 3rd coin could still land heads or tails. Heads, tails on the first 2. That does not change, the possible outcomes on the 3rd coin. Tails, heads on the first 2 does not change the possible outcomes on the 3rd coin. Tails, tails on the first 2 does not change the possible outcome on the 3rd coin. And if I include my probabilities here, the probability of getting heads here is 1/2 again. I'll just put that in red just so we can see it nice and clearly. 1/2. The probability of getting tails here on the 3rd one is 1/2. Notice it doesn't matter that it was heads, heads. It's still a 1 in 2 chance of getting a tails. It doesn't matter that it's heads, tails. There's still a 1 in 2 chance of getting heads. 1 in 2 chance of getting tails. And that's the same one. Notice I'm just writing those little probabilities in over the branches. And that's the question actually answered. The question was to draw a tree diagram for this experiment, flipping a fair coin 3 times. That's done. I want to look at something called the sample space. And the sample space, which we usually just denote with the letter S, is just a set. So I'm going to give it set brackets containing all possible outcomes here from 3 flips of a fair coin. So let me look at the first possible outcome, which is down here. It's along this first branch. Heads, heads, heads. That will be my first possible outcome. My next possible outcome would be heads, heads, tails. And we can follow the tree diagram along to figure out all possible outcomes. My next one would be heads, tails, heads. And heads, tails, tails, just following the branches along. My next one here, tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. And those are all my probabilities for the tree diagram for this experiment. Sorry, they're all my possible outcomes. So each of these is called an outcome. It's a possible result when I carry out this experiment. Remember, the experiment was flipping a fair coin 3 times. Note, there are 8 possible outcomes in here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, if you prefer to put those kind of in brackets, you know, absolutely you can do that. So you'll often see those in brackets like that within the sample space. That's absolutely fine. So 8 different possible outcomes when I conduct this experiment. Suppose I want to find the probability of one possible outcome. Suppose I want to find the probability that I get tails, tails, tails. Look at the notation. I just write P, TTT. We read that as P of TTT, or the probability of tails, 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 really. And to find the probability, well, given that it's a fair coin, the probability of tails on the first is a half. It's still a half. It's still a half. What I can do here is I can just, it's tails on the first and tails of the second and tails of the third. The probability of tails on the first and tails on the second and tails on the third is a half by a half by a half. I just take probability of tails on the first is a half, probability on tails on the second is a half, probability of tails on the third is a half by a half by a half is 1 over 8. So there's 1 in 8 chance that when I flip 3 coins, I'll get 3 tails. So it's 7 times more likely. There's a 7 in 8 chance that I won't get 3 tails. So if I was a betting person, I would not bet that on somebody to flip a fair coin 3 times and get 3 tails. It would not make sense. Okay? So that's my sample space for this experiment. So tree diagram just showing me all the different outcomes for each task in a statistical experiment. Remember, there's the different outcomes for task 1. In task 2, the outcomes are heads or tails. In task 3, the outcomes are heads or tails. Look at the total number of possible outcomes. There was 2 tasks, 2 ways I can complete task 1. There were 2 ways I can complete task 2. There were 2 ways to complete task 3. But as I build this tree diagram, you know, we're doubling the number of outcomes each time. So 2 outcomes from 1 flip of a coin, but 4 possible outcomes from 2 flips of a coin. And 8 possible outcomes from 3 flips of a coin. Notice 2 by 2 by 2 is 8. And this is something called the fundamental principle of counting. And the fundamental principle of counting says this: the number of ways a statistical experiment can be completed is equal to the product of the number of ways each task can be completed. 3 tasks here: flip a coin, flip a coin, flip a coin. Task 1 can be completed in 2 ways. Task 2 can be completed in 2 ways. Task 3 can be completed in 2 ways. So there are 2 by 2 by 2, 8 ways to complete task 1, followed by task 2, followed by task 3. Okay. Okay, I want to draw the tree diagram for this experiment. Choose a 2-course meal from a menu with 3 starters and 4 main courses. So there are 2 tasks here. Task 1 is to choose a starter. Task 2 is to choose a main course. There are 3 ways I can choose a starter. 1, 2, 3. And those starters, let's just call them starter A, starter B, and starter C. Now, I'm not going to fill in probabilities here because really it's not like flipping a coin. What makes somebody choose a starter, we don't know so much about that. This is kind of something slightly difficult, not more difficult, but slightly different. In order to find out, the probability that someone chooses starter A, I'd probably go and see how many people choose starter A each day, and then start to build a kind of picture of which is the most popular starter. But I'm not going to bother filling in any probabilities here because I haven't done that work. With the coin, I can say exactly it's 1 or 2. That's classical or theoretical probability. So there's 3 starters. Notice there's 3 ways to complete task 1, and then there's 4 main courses. There'll be 4 ways to complete task 2, so there'll be 12 ways to complete the experiment altogether. Task 2 is to choose one of the 4 main courses. And let's call those main course 1, main course 2, main course 3, and main course 4. So I could choose starter A with any one of those main courses, but I could also choose starter B with any one of those main courses. And I could also choose starter C with any one of those main courses. And if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The tree diagram starts at a point, triples, and then quadruples. So there's 12 possible outcomes from this experiment. The sample space would be A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, where each of those A, B, and C represent some starter, and each of 1, 2, 3, 4 represents some main course. Okay, so there's 12 different ways I can choose a 2-course meal in this case. What's the probability of choosing A3? Well, I don't really know what that is unless I go and, take some evidence that has been collected and seen, how popular is starter A, how popular is main course 3. Then I could start thinking about the probability that a randomly chosen person selects starter A with main course 3. But I don't really know that yet. I haven't gone and done the work. So that's really all I can say. If I wanted to draw out my sample space, well, let's just do it. My sample space would have the following: A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4. So there are tree diagrams and the fundamental principle of counting. I've got to be able to draw tree diagrams. I've got to know the fundamental principle of counting, the number of ways to complete an experiment. To calculate it, we just take the number of ways to complete each task within the experiment and find the product of each of those numbers. Okay. So have a look at some of the work on tree diagrams and the fundamental principle of counting. Okay. As the numbers of things include, if this was, I had 10 starters and 20 main courses to choose from, all of a sudden you'd have 200 different things. The tree diagram would become very impractical in that situation. So tree diagrams are handy when there's a small number of ways to complete a small number of tasks.